For this video, kita akan tengok Rydberg equation. So, Rydberg equation kita guna untuk cari wavelength. So, the wavelength emitted by the transition of electron between the two energy level is calculated by using Rydberg equation. So, 1 over lambda adalah wave number. So, kita rearrange untuk find wavelength lambda. Formula dia sama je dengan delta E, cumanya yang beza value Rydberg constant dan N1 dan N2. So, please take note, N1 adalah the lowest energy level, nombor yang lebih kecil. N2 adalah the highest energy level, which is the excited state. So, ini yang opposite daripada formula delta E. So, please take note perbezaan ini. And bila Rydberg constant, RH kamu akan pakai 1.097 exponent 7 per meter. And then lambda adalah wavelength. And the value always positive. And that is why N1 mesti kecil daripada N2. So the different value of Rydberg constant and its usage. So the first one 1 over lambda. RH dekat sini kita akan guna value, kalau kamu tengok kat sini Rydberg constant ada dua, 1.097 dengan 2.18. So tengok unit dia per meter ke joule. So kalau per meter ni kita guna untuk 1 over lambda, joule untuk delta E. Right? So please take note ada dua formula with different Rydberg constant. And kalau untuk cari lambda kita guna per meter tu. And N1 mesti kecil daripada N2. And untuk delta E mesti unit Rydberg constant kamu adalah in joule sebab in energy. Untuk delta E kita tengok initial the highest state and then final tu adalah the lowest state ataupun the ground state. Okay, so masukkan dalam formula kamu akan dapat. So why delta E negative? Because energy is being released in form of photon. So sebab tu negative. Right, so for example 1, calculate the wavelength of the fault line in the Balmer series of hydrogen. So fault line hint dia in Balmer series is the transition of electron from n equal to 6 to n equals to 2. So kalau nak cari wavelength kita guna formula 1 over lambda, which is the wave number lah. So ini formulanya. Masukkan sahaja value, substitute dalam this formula and make sure N1 mesti kecil daripada N2. So bila masukkan dalam formula, make sure you choose the right Rydberg constant, 1.097 exponent 7. Ini yang per meter tu. 1 over 2 to the power of 2 minus 1 over 6 to the power of 2. So masukkan dalam calculator, kamu akan dapat value 1 over lambda. So bila nak cari lambda, which is the wavelength, so just tekan calculator 1 over answer and then you will get your lambda 4.10 exponent negative 7 meter. So mesti unit meter. And kalau minta in nanometer, you just change to nanometer and the answer will be 410 nanometer. So just do the conversion. For this example, calculate the wavelength of energy liberated of the third line in Balmer series. So for Balmer series, ground state dia berapa? So ground state of Balmer, ingat Lehman balik. So ground state-nya adalah n equals to 2. So n final dia maksudnya n equals to 2. So third line of Balmer series tu berapa? Start daripada mana? Dia punya initial. Since Balmer series ground state dia adalah n equal to 2, so you draw the energy level and then make sure gap semakin closer to one another as you increase the number of n. First line transition 3 to 2, second line adalah transition 4 to 2, and then the third line is transition from n equals to 5 to n equals to 2. So itu adalah third line of Balmer series from 5 to 2. Okay, so kita dah tahu by using this method, ataupun kita boleh guna cara lagi satu, lagi senang. N equals to 2 adalah Balmer series, ground state untuk Balmer. So dia initial daripada mana kita nak tahu. Okay, so another method untuk kita tentukan N berapa. So ground state tambah nombor yang dekat sini. So kalau third line tambah 3 lah. Kalau dia cakap fourth line, then tambah 4. Kalau fifth, dia cakap tambah 5. So in this case, sebab dia cakap Balmer series And you know that ground state of Balmer series is n equals to 2. So ambil 2 tambah dengan third line. So third line maksudnya tambah 3 lah. So kat sini n initial will be n equals to 5. Electron drops to ground state n equals to 2. Okay, so ngam lah, sama je mana-mana method, you will get the same answer. So bila masukkan dalam formula, you just substitute 1 over 2 to the power of 2 minus 1 over 5 to the power of 2, and then for 1 over lambda you will get, and then 1 over answer, kamu akan dapat wavelength or the lambda, it will be 4.34 exponent negative 7 meter. And if the question asks you to convert into nanometer, so your answer will be 434 nanometer. So for the next question, determine the wavelength in nanometer, and then the second one determine frequency, and then next determine the energy that associated. So ini adalah delta E. So kamu nak cari 3 benda ni, you can use formula Rydberg equation, and then before that, okay, you need to interpret apa maksud soalan ni. Associated with second line in past chain series of hydrogen atom. So ingat balik, Leman balik pasar, and then break, putus. Okay, so for past chain series, ground state ni adalah 1, 2, 3. So for past chain, ground state nya adalah 3, and macam mana initial energy level tu berapa? So kita nak tahu n di sini berapa, n initial. So 3 ground state plus dengan nombor yang dekat sini, so plus 2. So kamu akan dapat value dekat sini 5. So the transition of electron that will form this second line in past chain series is the transition of electron from n equals to 5 drops to n equals to 3. Okay, so to find 1 over lambda, kamu akan masukkan value dalam this formula, substitute the value, and then you will get the answer 1 over lambda equals to 780088. Okay, so this is per meter, and for lambda your answer will be 1.2819 exponent negative 6 meter. So to find frequency, you can use this formula. Frequency equals to speed of light over wavelength. So speed of light 3 exponent 8 ms negative 1, and then lambda here is this one lah, kita ambil yang unit meter. We'll cancel off the unit meter, and your answer will be in per second. So ngam lah dengan frequency. Your answer will be 2.34 exponent 14 per second, ataupun boleh juga tulis unit hertz. Okay, so the last one, delta E. So delta E equals to hc Planck constant times speed of light over lambda. Okay, so for delta E, the unit will cancel off, meter with meter, per second with second, leave you with joule. So kamu akan dapat your final answer in joule, 1.55 exponent negative 19 joule. And since ini adalah transition of electron from n equals to 5 drops to n equals to 3, means you are releasing energy in form of photon. So delta E di sini mesti negative. So remember, kalau guna formula ni and tambah sahaja negatif di hadapan. So this is your final answer for delta E. Determine the wavelength, frequency and energy associated with last line of hydrogen spectrum in Lyman series. So last line ni macam mana terhasil? So we have ground state n equals to 1 and it is from infinity. High level dia adalah n equals to infinity. So kita boleh cari wavelength, frequency and energy by using the first one. Kita cari wavelength dulu guna 1 over lambda Rydberg equation tu. So when you have your Rydberg equation, you can find this last line which is the convergence limit. Okay, so the formula is 1 over lambda Rydberg constant and then n1 mesti kecil daripada n2. So substitute kan the value Rydberg constant and make sure you choose the right Rydberg constant, and 1 over 1 to the power of 2 minus 1 over infinity. So 1 over infinity tu is equal to 0. So kalau kamu tak faham, infinity tu adalah nombor yang sangat-sangat besar. So imagine 1 over 9999999. Your answer will be approaching 0. So 1 minus 0 equals to 1. So therefore 1 over lambda. For this formula, bila kamu substitute and tekan calculator, kamu akan dapat 1.097 exponent 7 m per meter, and then tekan 1 over answer, kamu akan dapat lambda which is the wavelength 9.116 exponent negative 8 meter. Okay, so tekan 1 over answer, jangan lupa. And then if the question asks to convert in nanometer, so kamu akan dapat this as the final answer. Right, so next frequency pula, guna this formula, frequency equal to C over lambda. So masukkan dalam formula and make sure you masukkan lambda which is yang unit meter, bukan nanometer, so that you can cancel off the unit and then your answer will be 3.29 exponent 15 per second ataupun hertz. So the next one is energy. So masukkan dalam formula delta E equals to Hc over lambda. Substitute all the value for the constants and then divide with the lambda in meter, and your answer will be 2.19 exponent negative 18 joule. And for delta E, make sure you letak negative sign to indicate the energy is being released. Next question, an electron in the hydrogen atom makes a transition from a higher energy level to n equals to 2. So daripada n unknown drops to n equals to 2, dia punya ground state. If the photon emitted has the wavelength of 410.2 nanometer, what is the value of n? Yang higher energy level tu berapa? So we can draw ataupun interpret daripada soalan, keluarkan dia punya facts. So you want to find n initial berapa. So to find dia punya n of the higher energy level, we can use Rydberg equation since you are given with wavelength. So the wavelength 410.2 nanometer, you convert into meter. So you will get 410.2 exponent negative 9 meter. Okay, so from here you can directly substitute into the Rydberg equation. 1 over lambda 1 over 410.2 exponent negative 9 meter is equal to this, and then you substitute into the Rydberg equation. So 2.4378 exponent negative 6 equals to, guna Rydberg constant 1.097 exponent 7, and then 1 over n yang pertama which is the ground state, the lowest number, 2 to the power of 2, and 1 over n2. Ini yang kita nak cari, to the power of 2. So n higher level itu yang akan jadi unknown. So rearrange your equation to find this unknown n. One over n to the power of 2 equals to 0.02771 n to the power of 2, and then rearrange to get n to the power of 2, 36.0067. Therefore, n you square root the number you will get, n equals to 6. So that means the higher energy level is the electron transition from n equals to 6 drops to n equals to 2. Next question, in the hydrogen atom, an electron transition from higher to lower energy level will emit photon with a wavelength of 1282 nanometer in Paschen series. Remember the mnemonic, leman balik pasar, break putus, and Paschen is the third one. So means ground state untuk Paschen must be n equals to 3. Determine the energy level for the excited state and then state the radiation region. Okay, so kita nak tahu n initial, which is the higher energy level, elektron tu jatuh daripada n berapa. So itu yang kita nak cari, and you are given with information in wavelength 1282 nanometer. Okay, so from the information, tukar nanometer pergi meter. So kamu akan dapat 1282 exponent negative 9 meter, and then you can substitute into the formula ataupun you convert pergi 1 over lambda dulu, cari dia punya value, dan baru masukkan dalam the Rydberg equation tu lah. Substitute the value for Rydberg constant 1.097 exponent 7 and 1 over n1 to the power of 2, which is the ground state, and 2 yang kita nak cari. So this n2 kita akan rearrange the equation to one side and kita akan solve for the unknown. So 1 over n2 equals to this, n2 will be 24.99, n will be approximately 5. From here we know that the higher energy level n adalah n equals to 5. The higher energy level is n equals to 5. State the radiation region for this transition. So ini it belongs to infrared region, since Paschen in spectrum region dia adalah infrared region. Next, figure below show the first 4 line in bracket series. So first kita kena cari biggest gap between the two lines. So ini kita nampak the biggest gap, therefore line D adalah the first line, C second, third and fourth. So ground state untuk bracket pula, tulis semula leman balik pasar break putus. So bracket BR break bracket 1 2 3 4, so means dia punya ground state adalah n equals to 4. Alright, so apa yang kamu kena buat, tulis dekat bahagian bawah ni 4. So that means all the transition of electron, macam mana hasilkan line ni, semuanya elektron jatuh ke ground state n equals to 4. So bahagian atas ni pula kita tulis the first line, macam mana kita hasilkan first line, hari tu kita dah belajar. So it start from 5, 6, 7 and 8. Okay, so boleh refer balik video sebelum ni. Next, state the region. So ini break bracket, it belongs to spectrum region infrared. So just state semula, jawapannya adalah infrared region. And then next, which line correspond to the shortest wavelength? Tulis semula relationship delta E equals to HC over lambda. So kita nak wavelength yang the shortest wavelength. Untuk cari shortest wavelength, tengok relationship, delta E semakin besar, wavelength semakin kecil. So line A adalah the shortest wavelength. Okay, next, so wavelength untuk line A, macam mana hasilkan line A? Daripada electron transition from 8 to 4. So masukkan dalam value, N1 4, N2 adalah 8. And then press your calculator, you will get this value. And don't forget to 1 over your answer to get wavelength or lambda. Your answer will be 1.9447 exponent negative 6 meter. If the question asks you to convert to nanometer, then your answer will be 1944.7 nanometer. Next question, determine the transition of electron that will produce green line with wavelength 486.3 nanometer. So if you see color, green line, blue line, yellow line, any color, that means it is Balmer series. So for Balmer series, we know that the ground state adalah n equals to 2. And Balmer series ni, it belongs to visible region. So if you want to determine the transition, kita kena determine from n equals to berapa drops to n equals to berapa. Ground state-nya adalah 2. Okay, you are given with wavelength, so kamu boleh terus substitute value wavelength lambda into this Rydberg equation and solve for n2. Okay, so for this question, kita nak tahu n2, which is the excited state, higher state tu n equals to berapa. Ground state kita dah tahu n equals to 2. So 1 over n2 to the power of 2. So rearrange this equation, sama juga macam soalan sebelum ni. Kita nak cari n higher energy level berapa. So kamu akan dapat n equals to 4. That means the transition of electron that will produce the green line is the transition from n equals to 4 to n equals to 2. Next part of the video, it is about ionization energy. So you can interpret this definition into this equation. Okay, so it is minimum energy required to remove 1 mole of electron. Here you are removing 1 mole of electron from 1 mole of gaseous atom or ion. Okay, right. So hydrogen atom, it is said to be ionized. Dia akan jadi ion when electron, you remove electron from its ground state. So it is from n equals to 1 to n infinity. So at n infinity, the potential energy for the electron, it is equal to 0. Here, the nucleus attractive forces, okay, between nucleus dengan electron, it has no effect to the electron. Tarikan tu adalah sangat-sangat lemah sebab elektron sangat-sangat jauh daripada nukleus. So the electron is free from the nucleus force of attraction. Okay, finding the ionization energy, so ini yang kita panggil sebagai convergent limit. So convergent limit is the wavelength or frequency at which converging spectral line merge together because of the difference between energy level become smaller and smaller. So you can see here the gap are getting closer and closer, means the difference in energy level are smaller. So IE or ionization energy is determined by identifying the wavelength of the convergence point or convergence. Okay, let's say tadi dia punya ground state adalah n equals to 1 and then dia punya higher energy state adalah n infinity. Okay, so to determine the IE, energy need, okay, energy required by 1 electron. Delta E equals to Rydberg constant times 1 over n initial to the power of 2 minus 1 over n final to the power of 2. Kita boleh solve kan and then substitute all the values. So when you solve this part, dia akan jadi 1 minus 0. Okay, kita dah buat latihan ni before this. and you will get back this value 2.18 exponent negative 18 joule. Okay, so this is the energy needed for one electron. Okay, so for ionization energy, it is energy required to remove 1 mole of electron. So kita masukkan dalam formula energy for 1 electron 2.18 exponent negative 18 joule times the number of electron in 1 mole. So remember, ini kita dah belajar in chapter 1. 1 mole is equivalent to 6.02 exponent 23. Okay, so ini Avogadro number. So 1 mole is equivalent to 6.02 exponent 23 number of electron for in 1 mole lah. The answer here, when you times this two, kamu akan dapat 1.312 exponent 6 joule per mole. So ini untuk setiap 1 mole. So mesti ada per mole. And then if you simplify this part to kilojoule, you will get your answer 1312 kilojoule per mole. Okay, so remember, kalau melibatkan IE, ionization energy, your final answer mesti in unit kilojoule per mole. Okay, let's have a look at this example. So for this example, you are given with Lyman series for this hydrogen spectrum, and it is shown here. Calculate the IE for the hydrogen from the spectrum. Okay, so untuk this part of this formula, okay, I will separate it so that you can see clearly. So untuk dapatkan Hc over lambda, it is also equals to H Planck constant times speed of light times wave number. So kamu akan dapat this simplified into this Hc over lambda. Okay, so you already know the value for Planck constant, speed of light, and also 1 over lambda wave number. You can get it from this spectrum. Okay, this line spectrum. So you can find delta E when you substitute all this value, and then you can calculate for ionization energy berapa kilojoule per mole. So when you substitute all this value and solve for delta E, kamu akan dapat the value 2.18 exponent negative 18 joule. And when you want to calculate for ionization energy, 2.18 exponent negative 18 times with 6.02 exponent 23 mole. So you will get your answer 1.312 exponent 6 joule per mole equals to 1312 kilojoule per mole. So this is your final answer for this question. Okay, so untuk this value 1 over lambda, kita pilih yang paling hujung di sini. Okay, the nearest to the convergent limits. Okay, however, Bohr's atomic model yang kita belajar ni, dia ada beberapa kelemahan ataupun kita panggil sebagai limitation or weakness lah for this Bohr's theory. So what are the weaknesses? So the first one, it could not be extended to predict the energy level and spectra of atoms and ion for more than 1 electron, yang mempunyai lebih daripada 1 elektron. Kita tak boleh predict. That means it can only explain for hydrogen spectrum or ion that contain 1 electron sahaja, contohnya helium ion. Okay, so sebab tu semua yang kita belajar semuanya melibatkan hydrogen spectrum. The electrons are restricted to move in a certain distance around the nucleus of an atom. this Bohr's theory also unable to explain the formation of extra line in the hydrogen spectrum. It also unable to explain the dual nature of electrons. So highlight this important keyword, or ions that contain more than one electron. So maksudnya dia hanya sesuai untuk hydrogen dan helium ion sahaja, and the electron are restricted to move at certain distance around the nucleus of an atom. And then it also unable to explain the formation of extra line and unable to explain the dual nature of electron. Okay, so what is the dual nature of electron? Okay, in 1924, Rydberg proposed that not only light but all matter has dual nature, which means it possesses both wave and particle-like properties. So he deduced that the particle and wave properties of an electron are related by this expression. Hence, this equation, it allows us to calculate the wavelength of an electron or a particle with mass and moving at a velocity. So itu yang dimaksudkan dengan it possesses the dual nature of electron. It possesses both wave and particle-like properties. Now let's have a look at Heisenberg's uncertainty principle. So Heisenberg, he showed that it is impossible for us to know simultaneously both momentum and the position of a particle such as an electron. So he come with a principle, which is this Heisenberg uncertainty principle. If the object is large, m is big. Therefore, delta x and delta p will be very small. So we can determine the orbit, which means we can determine the position and momentum. Okay, but if the object has mass of an electron, m will be extremely small. So these two values will be significant. So we can never describe how electron move in an atom. When we apply this uncertainty principle to the hydrogen atom, we can see that in reality, the electron does not orbit the nucleus in well-defined path like we think it is. So apa yang kita fikir sebelum ni, elektron mengelilingi nucleus dalam orbit, it is not very accurate lah pemahaman itu. So we cannot point where it is, mana electron tu, and how the electron move exactly. We can only calculate the probability in finding the electron in a certain position and at certain time. The region in space within which there is a high probability of finding an electron in an atom or molecule, it is known as orbital. So orbital ni yang kita akan belajar next subtopic. So kita dah belajar Bohr's atomic model and apa weaknesses of Bohr's atomic model, and this de Broglie postulate yang menentang pendapat ataupun Bohr's atomic model. Okay, and also Heisenberg uncertainty. We come to the conclusion, elektron, kita boleh tentukan dekat mana elektron tu at in a certain position at certain time, and the region di mana elektron itu berada kita panggil sebagai orbital.